All right, this scenario is kind of working with orbital data for Jupiter's moons, and we're assuming that the orbits are circular, which is a kind of not correct assumption, but it is something that we can play with the data and kind of track with it. So the first thing is just squaring orbital periods and orbital radii. I'm assuming that you can do that all yourself. If you literally just take the number on the left here, square it, and you'll get those results on the right. So part A says write an algebraic expression for the gravitational force between Jupiter and its moons. This is just our standard universal gravitational constant. So Fg equals g times the mass of, we'll say, Jupiter times the mass of the moon divided by the radius squared, which again, orbital radius is right here, so we'll put that in as a capital R. So simple, just the universal law of gravitation. So using your expression from part A and the assumption that the orbits are circular, derive an equation for the orbital period time t of a moon as a function of the radius r. So we're going to start with our expression here of Fg is equal to g mj mm over r squared. So we have to start with our expression that was given, and this is just the force of gravity. Then we're going to set that equal to our centripetal acceleration. So g mj m moon over r squared is equal to m moon v squared over r. And this is setting it equal to the centripetal force. Then we're going to have g times mj over r is equal to the mass, is equal to v squared. And this is canceling like terms. So getting rid of that mass of the moon, getting rid of one of those powers of r. Now, here's where it gets a little bit tricky. I'm going to write this off to the side. V equals 2 pi r divided by t. And that's just from knowing the path length is going to be 2 pi r, and the time t is how long it takes to go around the period. So the velocity is just the distance divided by the time. So we'll include that. Mj over r is equal to 2 pi r over t. So this is by using v is equal to 2 pi r over t. Sorry, whoops. So then we can just algebraically rearrange here. And I'm actually I've got an extra step in here if you like. So t squared is equal to 4 pi squared r cubed over g mj. Again, that's algebra. You can check that, but that's the idea here, is if we have this relationship, we get our thing. So which quantity should be graphed to yield a straight line whose slope could be used to determine the mass of Jupiter? So in this case, it would actually be useful to rearrange and solve for Jupiter. So I'm going to just do that here for a second. The mass of Jupiter is equal to 4 pi squared r cubed divided by g t squared. So if we look, 4 pi squared over g, that's all a constant. But r cubed and t squared, if I find the slope of that graph, that will give me the mass of Jupiter, r cubed and t squared. And that's just from looking at that equation of the mass of Jupiter is equal to a constant times r cubed over t squared. Complete the table by calculating the two quantities to be graphed, label the top of each column, including units. So if we go back up here, you'll notice they asked for that here. So t squared, r cubed, they give you the units already. Plugging all that in, then when you graph it, I'm not going to graph this perfectly. I'm just going to look off the answer key and give you a rough idea. So we got something like this, something like this, something like this, and something like that, roughly speaking, is what you should end up with. And then if I insert a line here, it should be, well, we know it should fix at 0. It should go something probably about like that. Then it says, and then the labels will have radius cubed, period squared. That all looks great. 2 identical probes are sent to Jupiter's moon. Probe A has a geosynchronous orbit. Probe B rests on the surface of the moon and rotates with the moon. Rank the magnitude of the following gravitational forces from greatest to least if two quantities are the same. Say so. So we know the greatest force would be whatever we're closest to a gravitational source. So force of moon on probe A, force of moon on probe B, force of probe B on the moon, force of probe A on the moon, force of probe A on probe B on probe A. Okay, so what we've got is essentially probe, Jupiter probe, and then moon probe, something like this. So we'll call this probe A and this probe B. So now, anything interacting with the moon is going to be much bigger than the probes interacting with each other. And so when you're, and that's just because there's so much more mass of a moon than a mass of the probe. So we're looking at first, all these ones that involve the moon, we know those are going to be our greatest. And then at the end, we're going to have probes acting on each other. So let's rank those lastly. So E is going to be equal to F. And that's just because there's so much less mass involved. Now, the moon pulling on probe A versus pulling on probe B, it's going to pull on probe B much stronger because it's closer. So the moon pulling on probe B and B pulling on the moon, well, by Newton's third law, we know those have to be the same. So B is going to equal to D, and that's going to be greater than the moon pulling on probe A, which should be equal to A pulling on the moon, which will be bigger than the probes pulling on each other. And we just talked through that reasoning. Anything involving the moon, by definition, has to be much larger than anything involving just the probes. That puts the probes at the least. Then if we look at, the relative distances of A and B to the moon, whichever is closer is going to be pulled stronger. Therefore, B is going to be pulled stronger. Let's take a look at the next problem here. So we have Angela, Blake, and Carlos studying data to the right, which shows the mass, orbital radius, and orbital period of 4 planets. They note that the period increases, but disagree why this happens. Here are their arguments. And so Angela says it appears the more mass a planet has, the longer its period is. More massive, more difficult to move, therefore they move slower. Blake says no, the planets move at the same speed, but planets with greater orbital radius must make a longer circumference orbits, therefore the periods are greater. So in other words, they're all moving at the same tangential speed. And Carlos says, it is the case that the further planet radius must have farther circumference orbits, but the farther planets also go slower because there's less gravitational force acting on them. So first, we want to create an equation that relates gravitational and centripetal force and speed and period, blah, 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 all of that together. So first, we need to start by just declaring Fg. And that's going to be G, m of the planet times m of the sun divided by the radius squared. So that's just, gravity. And we know that this has to equal the centripetal force. So G times the mass of the planet times the mass of the sun divided by r squared is going to be equal to the mass of the planet times v squared over r squared. And this is setting Fg equal to Fc because that's the only thing providing it. With some canceling things out and cleaning it up a bit, we can get that, sorry, this should be mv squared over r. So canceling stuff out, algebraically rearranging it, G times the mass of the sun divided by r is equal to the velocity squared. So that's just algebra. And then if we remember, we're still working with this v is equal to 2 pi r over t, because we want to introduce the period and the radius somehow. So g is the mass of the sun divided by the radius is equal to 2 pi r over t squared. Doing some algebraic manipulation to kind of isolate t. We get t squared is equal to 4 pi r squared, r cubed, divided by g times the mass of the sun. Again, that's algebra. Write your explanations a little clearer, how this was rearranged, but I'm going through quickly just to do the outline for you. And then we lastly get t is equal to 4 pi squared r cubed over g times the mass of the sun. And so we see the relationship between the period and the radius of the orbit. So let's talk about what they said. So if we look at our solution, our equation, we look what Angela says, the longer the period is, because more massive objects are more difficult to move, so these objects have slower orbits. Angela is wrong. Mass of planet doesn't matter. We see that it's not, that period is not contingent on the mass of the planet. It's contingent on mass of the sun, but not the planet. And so Blake said if you are, all planets move at the same speed, but we know that's not right. V is equal to 2 pi r over t, not all same speed. So the bigger the radius, the bigger the speed. And he's just assuming that the speed has to be the same, but we don't see that anywhere. We just see that if you have a bigger radius, then you'll have to have a bigger speed or a bigger time. We don't know which is necessarily the case. And Carlos is ultimately correct because we do have less gravitational speed the farther we go. And we do see the bigger that the r is, the bigger the t is. And so you can add in the reasons why that matches up. Again, it's because we see the direct relationship of bigger r means bigger t, and we also know that farther away, as we see in that first step, means less gravity. And that wraps up this. So if you have any questions, let me know, but otherwise this gives you a brief overview.